let's look at a few examples of polynomials and what we can find out about them just from having their equation. So our first example is f of x equals x cubed plus 3x squared minus 10x. Okay. So this is given. We actually will be able to graph this function pretty accurately. We'll be able to tell the degree, the number of zeros, the end behavior, and a few other things. So the first thing that we want to do, if possible for a polynomial, is to factor it so that we can find the zeros. So factoring means we're going to first notice that there's an x in each term. So there is actually what's called a GCF, greatest common factor of x. So that would be x times x squared plus 3x minus 10. And then we're going to hope that this also factors. So this would factor into two binomials if it will factor. And so let's try x and x. We want something to multiply to be 10. Maybe it would be 2 and 5. And then we want one of them needs to be negative so that it's negative 10. We want it to be a positive 3 when we add the two numbers together. So we want it to be minus 2 and plus 5. Okay, so this is what's called factored form. So the first thing we would need to do is to factor. Okay, and then from here, we can tell a lot of things about the polynomial. So first of all, we'd probably be asked, what is the degree of the polynomial? Okay, we're going to get that from the standard form, and that is degree 3. That's the exponent that is the highest of all the terms. Okay. Therefore, we have a possibility of having how many zeros? Okay, the answer would be 3. We can have up to 3 real zeros there. And the zeros are the zeros of this function. So we're going to do x times x minus 2 times x plus 5, the function, and we're going to set it equal to 0. That will create our zeros. So that's why we wanted factored form. Notice that these 3 zeros are x equals 0, x minus 2 equals 0, so x equals 2, and x equals negative 5. Okay, what I'm doing is setting each factor equal to 0 to find out what number would make the whole equation 0. Okay, so I have 3 zeros, 0, 2, and negative 5. Okay. I also can tell what the leading coefficient is. And the leading coefficient in this case is 1. And that's just going to tell me whether which direction I want to go with the ends there. I also probably want to be able to graph the y-intercept. Oops. Y-intercept. So the y-intercept is plugging x equals 0 into the function. I usually think it's actually easiest to plug it into the original, the standard form of the function rather than the factored form, but you can actually plug it into either. So that's the f of 0. Okay, so that's 0 cubed plus 3 times 0 squared minus 10 times 0. So it's actually 0. So the y-intercept is 0, okay? And then we also want to talk about the end behavior. The end behavior. So as x approaches infinity, what is y going to do, right? And that was in that polynomial patterns, that introduction, right? So this is an odd degree. So we know that the ends, one end is going to go this way and one end is going to go this way. They're going to go in opposite directions. And because the leading coefficient is 1, is positive, we really just wanted to know if it was positive. We know that it starts on the left at negative infinity and it ends on the right at positive infinity. So as x goes to infinity, y goes to infinity. As x goes to negative infinity, y goes to negative infinity. Okay, So let's see how we can use this information to create a pretty nice sketch of our graph. So first, we're going to draw the zeros. So our 3 zeros are at 0, 2, and -5. Okay, and then our y-intercept is also 0, so we don't get to draw anything extra for that. And then we know that the ends are here and here from our end behavior. Okay, now the rest of this, we just need to make a max here, right? It's going to go through this number and it's going to go back through this 0 and a minimum here. Remember that if this was a degree 3, there should be 2 total maxes and mins put together. Okay, so the one thing that you don't ever really know from this is what this maximum and what this minimum are. That you will find those out in calculus, and then you can also just use your calculator to calculate max and mins, but you don't need to in this case. You just kind of draw them in. Okay, so that's the one thing you kind of don't know for this graph for accuracy. Okay, so before we finish this problem, I want to introduce you to another kind of notation for end behavior. Okay, and what that is called is limit notation. Okay, it really says the exact same thing as this, but then it just looks a little bit different. So this limit is the limit of f of x. Remember, the function was f of x. And then right underneath, you write as x approaches infinity, put an equal sign, and we figured out that y was infinity, right? It's up. So this is limit notation right here for the end behavior of the function. The other end is the limit of f of x as x approaches infinity. See how the x approaches infinity goes below? It's just a nice little math notation. You know how math loves notation, so just a little bit different. And, oh, sorry, I was talking and didn't write negative infinity, did I? So I meant as x approaches negative infinity over here, and that is negative infinity for y. Okay, again, it says the exact same thing as this stuff. It's just a little more compact. Okay,